And I will turn things over right now to our host for today, who's Natalie, joining us from Calgary, Alberta at the MindFuel office. Take it away, Natalie.
All right. So, excuse me, good morning, everyone. We're really excited, and I was listening to all the schools and students that are joining us today. So we're very excited to have a busy launch with all of you in attendance today. And we launched our game that we're going to demonstrate today, Mission Maple Leaf, to celebrate Canada's 150th anniversary. MindFuel's mission is all about inventions, innovators, and innovation. So we wanted to do something that would really bring acknowledgement to the fact that Canada has contributed many, many inventions. And today we're actually going to have someone who's going to talk about some very interesting innovations happening. So in a few moments, I'll introduce a very special guest speaker today. And as mentioned earlier by Stacy, we will also be demonstrating our game. So before we get started, though, I'd like to take a moment to give a warm thank you to our funding partners, without which we would not have had this game. So these are include the Government of Alberta, Alberta Innovate, and the Canadian Heritage Fund. And of course, a big thank you as well to our co-presenting partner, Partners in Research, without which we would not be presenting today. And personally, I'd like to give a very warm welcome to the students who have helped us. So first of all the students that are in attendance today for our launch, and particularly a very warm student thank you students, a note to two schools who've helped us throughout our user testing. And those schools are here in Calgary, Alberta. So we have Chila School, and we also have a school who I believe is in attendance, Renard School. So all the students in the class at Renard, if you could wave and just say a little something so we know you're there. So thank you, and I wanted to personally thank you for all the help you've contributed to our game. I promised you would get to see the end, so here we are today. So maybe just one last housekeeping note. I believe you have probably found by now the Q&A button. It should be at the top left corner. So at any time during our launch today, if you have questions for me or for our guest, or when we do the demonstration, please feel free to type the questions. I'll try to answer, get as many as possible as answered by Dr. Carmichael, who's our guest joining us in a moment. And we'll do our very best to answer some from all over Canada, as we're coast to coast today. So without further ado, I would like to welcome now Dr. Carmichael, who's joining us from the Department of Chemistry and Biochemistry at the University of Windsor. She's going to tell us of several fascinating things about flexible electronics. So Dr. Carmichael, thank you for joining us and welcome. And I'm passing the baton on to you right now.
Okay, well, thank you. And hi, everybody from across the country. This is really, really exciting. So what I'm going to do is I'm going to share some slides and talk to you about the type of research that we do in my lab at the University of Windsor. We're interested in materials chemistry and surface chemistry. So, but what I want to talk to you today is our work in wearable electronics. So in my group, which I have students who do research in my group, we're inventing new electronics that you can wear. And so I'm going to tell you a little bit about what that means and talk about some of the inventions that we're working on right now. So if we think about wearable electronics, the idea of wearing electronics on our bodies, it seems kind of new, but it's actually been around a really long time. So the first idea for wearable electronics came more than 50 years ago, which is amazing because we didn't even really have computers then. But back 50 years ago, this man, Hugo Gernsback, had the idea that instead of having your TV in the corner of the room, you could wear it and have your TV right up close and personal with you. So he actually built this device, and he's demonstrating it in this picture. He's got his TV literally on his face, and there's knobs on the front so he can tune in different programs, and you can see the big antenna so he can receive these programs over the air. So it was a really neat idea. It was really ahead of his time. And the problem is nobody wanted to wear it because it was so goofy looking. You have this giant antenna on your face and it's kind of bulky. But it was a really creative idea. And he was really known for this kind of thing, and he was really kind of a famous inventor. He was a pioneer of science fiction, and the Hugo Award, which is an award given for science fiction literature, is named after him. And you may have seen this on some of the books if you read science fiction. It's a very famous award. So 50 years ago, we had this idea, and it didn't go anywhere. Nobody manufactured these. Nobody went to the store to buy wearable televisions. But the idea never really went away. What we needed was some innovation to make it something that people wanted. And so if we look at what happened in wearable displays, they've evolved over the years, right? So we can look in 2014, we have this device called Google Cardboard, which looks kind of goofy. It's a cardboard box you wear on your face. But what's cool about it is that inside the box, you can put your smartphone, and you can run an app that gives you virtual reality experience. Right? So the technology is finally here that we can make really cool wearable devices. And so maybe we can dress up the wearability of it a little bit. So instead of using a cardboard box, we can make fancy VR goggles and wear them on our face. But really, it's funny if you look at this, all of the wearability of all of these devices is not that different. Back from 50 years ago to today, it's still a big bulky device that we wear on our face. And so what we look at in research is, how do we make wearable devices more wearable? How do we make them so that people actually will want to wear these things? So we're always asking in research, what's next? What are the next big ideas? And then how do we build those ideas? How do we actually do this? And so that's what I'm going to talk about. So for example, for wearable displays or wearable TVs, maybe what's next is a device that you could actually put right in your eye, like a contact lens. And it has the electrical components on the contact lens, so that you would have virtual reality right in your eyes. Let's look at a few more examples. Most of you have seen a Fitbit, right? You have a Fitbit, you wear it on your wrist. It tells you if you've, how many steps you've taken every day. And so this is today's device. So when we ask, how can we make this wearable more wearable? Maybe that could be a temporary tattoo that you just put on your skin, like shown on the right here, right? And in this one, this is a real thing. What's happening is the person is swiping their finger across the temporary tattoo and controlling the display on the computer screen in the background. Right? So this is something that you wouldn't even notice you were wearing. It wouldn't be a bulky thing. You wouldn't have to remember to put it on. It would just be part of your skin. There's lots of examples in healthcare. So right now, today, if you have a problem with your heart, then you might need to wear a monitor. So you put these sticky things on your skin, these electrodes on your skin, and they're connected with wires to what's called a Holter monitor. And you have to put that in your pocket. It's about, it's a little box. And you have to carry it around so it monitors what your heart is doing. And so when we think about what's next, this could be something like what's shown on the bottom right. This device is called a heart sock. And what that is, it's a device that's custom made out of a soft material to go slip right around an actual heart. This is being tested in animals. Right now, it's not used in humans yet. But you can see that what we have on the surface here is a bunch of little electrodes. These are made out of gold. And what that's doing is it's monitoring how the heart's moving in real time. So it's a soft device that just slips around the heart like a sock. And you don't even know it's there. Right? So these are research innovations for wearable electronics, making things more wearable. Another example is from virtual reality, where maybe we want to be able to interact with virtual reality. So when we move, our avatar in VR actually moves. So to be able to do that, we have to wear electronics that monitor how we're moving, right? And so people have invented these things, and you can see it here. But nobody really wants to wear a glove that looks like this, right? It's bulky, it's big. So when we ask what's next, this could be something like a glove that you put on that's made out of a soft material. So you don't have this hard plastic all around your hand trying to monitor how you're moving. So when we think about what's next, kind of overall, we're really talking about making electronics that are soft, like our bodies are. Right? So what kind of materials are soft, or what kind of things would we want to wear? That's one of the big questions. So we might want to wear something that's soft and stretchable and flexible, like rubber, like a clear rubber shown here, that you could just laminate on your skin. Or maybe you could just put on a pair of rubber gloves like my students wear them in the lab all the time. People who work in doctors' offices and hospitals wear them all the time. Maybe the glove could have electronics directly in it. And then the last example, of course, is clothing, right? We all, put on our clothes every day. And what if those clothes could have the electronics embedded right in the fabric? So you wouldn't even know you were wearing them. You would just put on your socks in the morning. Your socks would tell you how many steps you did. And telling, maybe transmit that to your phone. So these are the big ideas. And so what I want to talk about is how do we actually build things like that, and some of the work that we're doing to be able to do that. So when we think about electronic devices, one of the most basic things you have to have are metals, right? You have to have wires. So if you open up, if you were to open up your computer or open up any kind of electrical device in your house, you'd see metal inside it, right? Metal is what conducts electricity. And so what we have to do is we have to figure out at the very most basic step, how do we make metals that are wearable and conduct electricity while we're wearing them? And so I want to talk about some of the research that we do to be able to do that, right? So how do we make stretchable metal wires? So one of the things we know about metals, right? They're all around us. We know that they don't stretch. We have a fundamental problem here. The picture on the left shows you a piece of metal. If you could grab a bar of metal and stretch it, and you were super strong, and you could stretch that bar of metal, you wouldn't stretch very much, right? You wouldn't expect that. Metals aren't rubbery and soft. What happens is they break. So they form cracks, and then they break into two pieces. And we have lots of everyday examples of that. Metal pipes break, parts on different machines, if they're made of metal, can break. Even your braces can break, right? So if you have braces, your orthodontist tells you not to eat certain things because sometimes you can actually break the metal wire, the stainless steel wire that holds your braces in place, and that's a problem. So metals don't stretch. So how do we make metals stretch? Well, when we want to make them into devices, into stretchable devices, what we do is we make coatings of thin films of metal. So this is a picture of rubber that we coated with a film of gold. And you can see when we stretch it, there's kind of a pattern or kind of a texture to the surface of the metal. And if we could look closer, we'd see what's happening. And in fact, we can look closer. What we do is we look under the microscope. And when we do that, this is what the surface, on the bottom left, this is what the surface of that metal looks like. You can see these vertical lines that are all cracks. So when you stretch metal, when it's put on the surface of the rubber, it actually forms these big, long cracks that go all along the metal film, right? And so I have a little animation of that. So we can see in the upper right-hand corner, you have rubber coated with metal, and when you stretch it, you form cracks. And of course it cracks. That's what metal does, right? It can't stretch, so it breaks. And that's a problem if you want to make something electrical. Right? So once those cracks go all the way through from one side to the other, what happens then is what we call electrical failure. It means that electricity can't flow from one side to the other, right? So now the wire is broken and it doesn't conduct electricity anymore. It's the same as unplugging something from the wall, right? If it's not connected, there's no electricity flowing. So if we look at this again, here's the picture, my microscope picture of my metal film. I want to be able to pass electricity through it, right, to make it conduct electricity so I can make a device. But what happens every time when we stretch these films, everywhere there's a crack, it's like a little stop sign for electricity. You can't pass here. There's a gap. You can't go. So every single crack says stop to electricity flowing through the film. It means it's broken and we can't use it. So in research, we try to figure out a way around that. And it's really hard to make metal not crack. So in my research group, we decided, okay, the metal's going to crack. Let's change how it cracks so it can still conduct electricity through it. And so what we did was we found a way to make a metal film that when it cracks, when we look at the microscope picture, the cracks are these short little cracks that form. And so what this means is when we want to have electricity pass through the metal film, like before, instead of being broken, because it's cracked from one side to the other, there's actually all these little pathways. They're not straight pathways, but there's all these little pathways through the film for electricity to pass through. Okay, so now when we try to make this into a device, the electricity can get through from one side to the other, and we can actually make things that work. So once we have this, we can start to think about what can we build that's interesting, right? And what we can build are different devices that we test in our lab. So these are all things that we've made in my lab. The first one on the left is a wearable strain sensor. And what it means is the device is along the back of my student's thumb. And when she bends her thumb, the device can detect that her thumb is bending. And it lights up all of those LEDs as a way to, as like a signal. And so we can make a wearable, soft, bendable sensor. We can also make bendable and stretchable light-emitting devices. So this is a device that emits light. And the reason it works is because we've made this stretchable metal and put it in the device. And then finally, right now we're working on putting some of these metal films into gloves, so that instead of having something that we kind of tape onto the back of the thumb with some Band-Aid and some tinfoil, now we can have it right on a glove, and we can have a virtual reality glove that maps how the hand is moving, but it's really wearable. Okay, so, but not everyone wants to wear rubber gloves. We want to have electronics in our clothing. And so when we think about electronic fabrics, this is a really interesting kind of area of research. And it's something that people work on all the time at their home, not just at universities. You can buy things like this conductive thread, right? And this is a copper wire that you can sew into clothing and make light up clothing. So you buy all these little electrical components and you sew them in and embroider them into your jacket or your t-shirt, and you can make your clothing light up. And so an example of that is shown in the bottom left. And this is a glove that is a turn signal. So when you move your hand in this motion, what happens is the turn signal turns on and all the little lights that are sewn into the glove light up. And so you could wear this if you're out riding your bike and you want to use it to signal that you're turning left or right, like a signal on a car, but for people, that's wearable. Now, in order to build this, of course, we have to have all these components and all these wires, and we sew them into the clothing, and you can totally tell they're there. So in research, we are always asking, what's next? How do we make this even more wearable? And so our idea for clothing is to take the fabric and understand what fabric is, how it works, and put the metal directly in the fabric so that we can make devices that way. And so the first question we have to ask, of course, is, what is fabric? What does it look like? What are we working with? Right? So if you have a t-shirt and you have a look at it, you can see what fabric is made out of. And if you look at your clothing, right, you can, if you look really closely and have a look at your t-shirt, you can see that it's made of all these little stitches of threads, right? And they're all interlocked together. It looks something like this, right? And so if you have good eyes, you can see it probably looks like this picture that I'm putting up right now. It's got this kind of stitching pattern. Now, what does it look like if we can look even closer? Right? And in our lab, we can do that because we have microscopes. So we can take your t-shirt and put it under the microscope and see what it looks like. So when we do that, it looks like this. So you can see those threads all woven together. And if you look carefully, you can see that each of the threads that's woven together that you can see kind of with your eyes right now is made up of even smaller threads that you can't see with your eye. So what we can do is we can use an even better microscope and look even more closely at a t-shirt and see what it's really made of. And so what we use is something called an electron microscope. And when we do that, we can see that each of those threads looks like this. So each thread is made up of little tiny threads that you can't even see with your eye. You need a microscope to see it. So now we know what fabric looks like. What we want to do is put metal on it. So what we've done in my lab is we've taken each of these tiny threads and we've been able to coat them with metal so that we can put electricity through fabric and make devices. And so I'll show you what that looks like. It's really, really cool. So this is a picture of the fabric that we've coated with gold. It just looks like ordinary fabric that's kind of shiny, but it's electrically conductive. And the picture in the background is you can see the gold coating each of the little tiny threads. This is something that we just did in my lab the other day. And we can use this to make devices. And so what we've done is we've taken this gold coated fabric, and you can see a diagram up in the upper right, and we put some coatings on it. And now we can make fabric that lights up. So we don't have to sew little rigid components into the fabric. The fabric itself lights up and it emits blue light. And we can stretch it. So you could have this in your t-shirt and your t-shirt would glow. which is really cool. So we can think of, sort of fashion things we could do with this and interesting, ways to wear clothing. But also we can think about things like those turn signal gloves, making them even more wearable. So these are all the kinds of applications we're interested in, but we kind of do the fundamental science to make that possible, right? We figure out how to get that function into the clothing. So I am going to just wrap up here. So I just want to leave you with the sort of idea that as we make electric devices more wearable, we might have them on our bodies all the time. You might even go to sleep with electronics in your pajamas, and they'll tell you how, the electronic will tell you how you slept all night. So we think that the future of wearable electronics is soft because our bodies are soft, and that's a good thing. But we also think that, it's a lot of interesting questions about, how electronics will always be with us, and what kind of what our lives will be like when we get to that day. And finally, I just want to show you pictures of my research group. All of the stuff I showed you from my lab was done by the people, except me, I'm in this picture for some reason, but everybody else in this picture, all of my students, they do all of these experiments. So when you come to university, after about your first year, maybe 2 years of classes, you can get into a lab and you can work on the stuff like I showed you today. And you can have this kind of experience and do these kinds of inventions. So I'm going to finish there and answer questions or whatever we're going to do next.
Thank you so much, Dr. Carmichael. That was a very interesting, and what a great way, as we're celebrating 150 years of inventions, to kind of look into the future and see what the future might have in store for us in terms of invention. So I found that very interesting, and we already have several questions for you. So I'd just like to remind all the students in different classes, if you'd like us to be able to call out your name and answer the questions, it's even better if you could add the name of your school or your location. So for now, we have one first question from Sean Bradford, not sure what school. Sean's question is, why is gold used instead of other metals in the heart sock?
That's a great question. So we can use other metals for different things, but when we're putting things in the body or on the body, if the metal is going to be in contact with your skin, we use gold because it doesn't cause any reactions. So your body doesn't react to it. It doesn't give you a rash or anything like that. So gold is what we call biocompatible, and so you can actually have it inside your body, and it's safe.
And Lily Kwong, also another student, would like to know if we could use other types of metal on clothing.
Yeah, there's lots of different options that we can use. So what we want when we use metals, right, is we're thinking about, are they going to oxidize? Are they going to change over time? Are they going to react with the environment? So gold doesn't do that. So it's a really nice one to work on in the lab. But when we go to manufacture these things and you want to buy them, maybe we want to use something a little cheaper. So we look at things like copper and things like that are used more commonly, right? Copper wire is something everyone's seen.
That makes sense. Another interesting question here that I was actually wondering about myself. So let's see, where's our question here? So several students actually wanted to know what would happen. Could you incur an electrical shock wearing, for example, a shirt that has metal in it?
It depends on what you're doing, what you're trying to build. Generally, no. It just depends on, electrically what you're building. Some things we would want to insulate from the body, right? So we would put something around them so that they're not against your skin. But other things like the tattoos, right, like the things that are laminated on the skin to detect your motion, if we make them out of materials like gold, you can have them in contact with your skin without, problems like shocks and things like that.
We also have, let's see, there are several interesting questions that keep coming in here for you. So we have Douglas Shaw asked, why is new technology so expensive to buy? So this is from grade 4 in Muir Lake School in Alberta.
It's a great question. There's so much that goes on to make something like your smartphone that you don't see. And I think this is a really great area for kids to learn about. There's a million jobs you can do to invent and work on like the next generation iPhone. And that's what you pay for. right? There's all these people doing all this innovation, inventing things and coming up with ways to build things. There's engineers, there's physicists, there's chemists, all working together to build stuff like this. And so we pay to have all that innovation.
Definitely. And actually, in terms of the cost related to all that, we have a grade 5-6 class in Adelaide, Hoodless, Hamilton, Ontario. Sarah Kondo would like to know what happens if there is a malfunction while wearing electronics.
That would be bad. We wouldn't want that. What we want to do, there's a lot of really interesting issues that are kind of coming up. So we want to make things inexpensive and make them as cheap as possible so that if there was a malfunction, like maybe you damaged it or you got something on it that you shouldn't, that it wouldn't be super expensive to replace it, right? The other thing is about that is how do we protect these devices so that you can wear them and we have a lower chance of that happening. So in my group, we work on things like barrier layers and polymers that we can protect devices with to make them so that, you know, they're really durable and you can carry them around. And even if it rains, it would be okay.
Awesome. And I think we have time for maybe one last question. So let's see here. Grade 5 students from Sandhills, how long will it take to develop all of this technology?
That's a really good question. There's that's such a big question. There's so many things to invent. So in my lab, we do a lot of demonstrations. We can show technologies and make things, and they're really cool. And I showed you some pictures. But to make that a real product that you could go to the wearable electronics store and buy is a huge, long process, right? So it's going to be years and years before we're buying stuff like that. But it just sort of depends on how complicated. You'll get really simple things to begin with, stuff that's easy to make and that has good durability that people want to buy. But yeah, I guess I would just like to sort of use this as a way to say, look, there's so much you can do in the field. If you're interested in science, this is a great field to work in. There's so many problems to solve, and we need everybody's good mind to work on it. So I use that as a commercial for wearable electronics research and science and technology.
Well, I personally find your research fascinating. If I ever contemplate a second career, I think that would be the one.
Awesome.
So first of all, thank you so much, Dr. Carmichael, for joining us today and inspiring our students who are probably soon going to start thinking about what they want to do and what they want to contribute to, and gives us a good insight into what might be awaiting us in terms of inventions. We had many more questions we didn't get to answer. Perhaps we can relay some of those to you, but you've already answered a lot. So thank you so much on behalf of all of us here at MindFuel in Wonderville. And now, without further ado, we've talked a little about the present and the future, so we're going to have a look into the past and what we've created, what we've invented by playing a demonstration of our game, Mission Maple Leaf. So someone from MindFuel is going to be joining me. His name is Brent. You will not see him, but he will be the mysterious hand during the demonstration. So I'll be chatting with you as Brent explores the game. So let's let Brent begin his presentation here. Perhaps just so if you want to play the game, I will be sending you right now a link. So you have the option to either play the game, or you can watch the demonstration as Brent explores a few games for us.
What kind of sandwiches? Do they have the crust cut off? Because I hate the crusts. Why can't science engineer bread that has no crusts? I'm sorry, where was I? I should never narrate before lunch. Ah, yes. From that vast space, a distress signal comes from the planet to the SciCan satellite, high above Canada. A small robot named Electronic Dermatus Unit number 8200.38-66-G567.04, integer 2287 and 3/3.
Ed's fine. You can call me Ed.
Discovers a distress signal from the planet Tontar from his station on the SciCan satellite.
Hello? Yes, I am happy with my long-distance plan.
No, line 2.
Line 2. Line 2. Where is the button for line 2?
It's there, on the left. No, the other left. No, not... Answer the call, please. It's urgent.
Will you give me a second? Please. There. Hello? I can't hear you. There's interference from the black hole I'm somehow safely located near. I'm going to put you on video speaker. Hang on.
This is Commander Exposition of the planet Tauntar.
This is Ed. We read you. Go ahead.
We need your help, Psycan. Our planet is losing its natural resources. Nothing is growing. Communications are down. The conditions are harsh, making transportation difficult, and we are in need of new medical and agricultural innovations to help sustain our population. As you know, our entire ecosystem is almost exactly like your Canadian ecosystem.
Wow, convenient.
So we need your expertise and technology.
Hang on a second. I think I've got something that can help. Aha! Wait, no, that's not it. Hang on. Aha! Behold the Wapiti.
The what's it now?
It's called a Wapiti, a world-altering paradigm integrated technology interface. It's a machine that harvests and implements Canadian science, technology, and ecology and integrates it into similar ecosystems.
How?
It's complicated. Never mind that. I just need to find the right parts. Don't worry, I'll get right on it.
Thank you. The fate of Tauntar is in your hands. Help us, Psycan. You're our only hope.
I'm gonna need a little help here. Let's start by taking a closer look at the Wapiti. Okay, according to these schematics, there are 4 main parts we have to find. Let's take a closer look through our Canadian Innovations catalog and see what we come up with. Ah, I bet we could find something in one of those areas. Go ahead, choose an area to explore, and be sure to check out Innovation Timeline for more information.
So now that we've heard our introduction, Brent is going to choose probably 3 games for us to demo with you now. I have a good idea of which one he's going to choose.
The umiak is an open boat made with skin stretched over a wooden or bone frame created by the ancestors of the Inuit people around 1000 AD.
So now Brent's going to select different objects that were needed for the umiak. So the umiak, if you want to imagine what it was, think of a very long canoe, about 6 to 10 meters long, 1.5 meters across, that you could put your entire family in. So it was very important to assemble it with all the things you needed so you wouldn't sink. So that's what Brent's doing now. And soon we're going to see if he chose the correct objects.
Perfect! That'll work. Nice job!
So Brent didn't think. That's pretty good.
Umiaks were used to move families and their belongings between hunting grounds, as well as for the annual whale hunt.
So now Brent's going to try his hand at another game. I know that our students at Renard played most of these games we're seeing now, especially the umiak one that we just went through. Now we're going to play another one that we also got a lot of help on with our user testing. Let's see what Brent has in store for us now.
The telephone, invented by Alexander Graham Bell in 1867.
Well done! Wow, I didn't even see that one. Woohoo! Well done! Woohoo!
So obviously Brent has some experience on this game, I think. So the phone, invented by Alexander Graham Bell, is about 150 years old now as our country. And which reminds me, we have Wayne Gretzky Elementary School joining us today from Brampton, Ontario, which is where Bell lived. He was Scottish, but that's where he lived when he was here in Canada. So thought I would mention that. I think we have another school also from the same location joining us today. So what Brent's doing now, he's connecting different wires. That was necessary back then. We didn't have iPhones. It wasn't that easy.
Bell received many major awards, medals, and other tributes, and his name is recognized as one of the most famous inventors and scientists of all time.
And now we're gonna demo a third and last game for you. There's several games in our series of inventions, over 20 to be exact. So after our launch day, you'll get to try them all, but we're going to try a last one with you here that Brent will demo for us. It's a more recent invention. So now Brent is going to play our APXS game, which was a Canadian invention used at the end of the arm on the Mars rover. Very important to advance science in terms of chemistry and many other fields to understand the components on Mars and be able to determine whether there was life on that planet. So now Brent is assembling.
Here it is, the Mars rover Curiosity. On Mars, roving. On the end of the arm there is Canada's contribution, an instrument called APXS, which sits at the end of the rover's robotic arm and analyzes the chemical composition of Martian rocks and soil.
So Brent's getting pretty good at this game, assembled that pretty fast, collected the items, and now he's going to put them together.
That's it. Brilliant. That looks promising. Good old APXS. Good things come in small packages, I guess.
Awesome. All right. Good job, Brent. So now I'd like to take a little moment here to have some live questions from our school Renard, who spent a lot of time helping us. And I recognize, I'm going to recognize lots of you students there. Hopefully, you've enjoyed helping us with the game, and I know some of you have some live questions, so we're going to hear your questions live, and then we can, I don't know if the questions are addressed to Dr. Carmichael, if they pertain to the game, but we're all in attendance and waiting for your questions. So Renard School, are you there with us, and can you hear us?
Yes, we are.
All right. Are you in a good mood?
Yes.
Okay. So let's hear some of those questions.
You guys have any questions about the game?
Something you'd like to ask Dr. Carmichael, or anything you'd like to ask at all?
Yeah. This is actually about the wearable technology.
Awesome. We can hear you now. I think Dr. Carmichael is listening to you.
I am listening.
Okay, so when we're trying to make wearable eyeballs in the future, like remember so how long do you think we'll have to wait until we can get that in stores?
So you're talking about the contact lens that goes in the eye, right?
And like sort of cyborg eyes.
Cyborg eyes. There are some things like this already that are like prototypes, meaning that they're testing them with people. And one of them is a sensor for glucose. So you can get a contact lens that you put in your eye, and it's good for people with diabetes, so they can monitor the glucose levels in their tears of their eye. Things that are more complicated are going to take more time. So we're thinking, you know, sort of years out, plenty of time to do research, plenty of problems to solve in research and development. So it'll be some time before we have the real like virtual reality in your eyeball.
Awesome. So great question, and thank you for the answer. Another question here.
This is also about the wearable technology, actually. What would happen if the clothing got wet? Would it like short circuit or something?
That's a good question. We actually do some washing tests in my lab. So we make the fabric with the metal on it, and then we get some Tide detergent and we actually wash it and see if it still works. So depending on how you make it, you can make it still work even after washing. So we think that we'll be able to have things like t-shirts with electronics in them that you can throw in the washer and will still work. Which is, I think, really an important part of it, right? Because we have to wash our clothes. So building that into our designs is something that we work on.
Awesome. So we'll take one last question from Renard School, and then we're going to go visit Walter Gretzky Elementary School.
Again, this one is about the wearable technology as well. Would the wearable technology or like that, would it be its own brand, or would the actual wires and all that be implanted into bigger brands, say Expedia, for example, or something like that?
I think the answer is yes. It can be. It'll be many different things. So big companies like Intel are sponsoring wearable electronics research, and Samsung and places like that. They do a lot of this kind of stuff. But it'll be like anything else, right? There may be startup companies that work on it and sell products, and there are a lot of those now in Canada too. So yeah, I think it'll be a lot of components together.
Okay, thank you.
Thank you so much, Renard School. You've lived up to all your brilliant comments and questions that I had a chance to witness. And now we're going to move to Walter Gretzky Elementary School, or should it read Wayne Gretzky Elementary School? So our Wayne Gretzky Elementary School. So you guys are live, and maybe we'll take a few questions as well, and maybe a little wave to show us you're there.
Hi. I'm here.
Awesome. So let's hear the question.
When you put the thing in your eye, do you have to like keep on charging it with a battery? With a battery?
You would need to have, if you wanted to build something like that had a display, like you could watch TV in your eye, yeah, you would need to have some power. And that's one of the big topics in research is how do we do that? Could it be a solar cell? Could it be a little battery? Those are all things that we're inventing.
Very good question. How about another question from the Wayne Gretzky Elementary School? If you have no more, that's okay too. All right. Well, thank you to you guys as well, and thank you again, Dr. Carmichael, for answering these questions. And as we slowly move on to closing our launch with you guys, I wanted first of all to thank Dr. Carmichael again. I'd like also to thank all our funding partners. So of course the Government of Alberta, Alberta Innovates, and the Canadian Heritage Fund. Of course also our co-presenting partners in research, and probably a heartwarm and heartfelt thank you to all the students that helped us make this game a reality, and to all of you that are there listening today. So remember, we're doing this to celebrate Canada's 150th anniversary. So let's think of more inventions, more innovation that we can contribute to the future. And I challenge you to go play every one of those 20 games between now and July 1st. So thank you on the behalf of MindFuel in Wenderville, and we wish you a great summer. You're almost done. Summer vacations around the corner, and summer starts today. All right? So thank you, everyone, and see you for another video game.